obviously we're going to be talking about analytical chemistry exam questions and what's the best way to answer them. And why is that an issue? Well, there's a lot of confusion because in those exam questions, we just have all those spectra presented to us. We will have a hint or a cryptic clue, as some of my tutor students have told me they like to consider it in the past. So this is the text at the very beginning of an exam question where it says compound X is such and such, and it gives you just a clue. Compound X is an alcohol, or compound X has such an empirical formula. And by the way, here's some spectra. Tell us what the compound is. So there's all that data in spectra, but so few words to help us. So examiners expect us to explain what our answer is as well, not just say, well, the answer is this. You're expected to explain it. So some other things that can make this difficult are the subtopics. So the mass spectrometry, the infrared, etc., are taught separately during your school course. There's very often little teaching of using them together, how to use them in relation with each other, and little guidance of how you should write your answer. So you have the lesson on Proton NMR, for example, but you're not taught how to use that as in the answering of a question that has various other spectra as well. So we're going to try and sort that out today. Okay, so let's start with a golden rule. And this is a golden rule for all exam questions, in my opinion. And that is to pay attention to everything in the question. Pay attention to everything in the question. There's no redundant information in exam questions. What do I mean by that? Well, I mean that when you answer an exam question on the paper, the question does not give you anything other than the information you need to use. It will not give you superfluous information. So where you see something presented to you in an exam question, you'll be expected to use it somehow. What else? So make use of every bit of information in the question, and something that's also forgotten is to make good use of the data sheet provided. What is the data sheet or data booklet? Well, it's certainly in the UK in A-level, we will get a data booklet with the exam paper. It's not just a bunch of constants and a copy of the periodic table. Those are there. They are useful, but there's more to it than that. So we often have infrared absorption values. We'll have the carbon-13 NMR chemical shift values. We'll have the proton NMR chemical shift values tabulated. The ones that we'll need to answer the questions anyway. And of course, we have the periodic table, which we'll need for working out relative molecular mass. So here's an example of the data booklet. So you can see this is from one of the A-level papers. So we have a bunch of constants, we have the abbreviation, and we have the value for those constants. So that's what you're expecting to see as in a normal data sheet. And then there's some extra information that helps down here, a little bit of information about temperature conversion and some mathematical conversions and prefixes, suffixes. Then also we've got an infrared absorption values table with some basic information. So we'll have the wave number of various ranges of peak, and we have the bond that is assigned to. So, for example, 500 to 600 would be the carbon-bromine bond. Also, we have the carbon-13 NMR shift table. And again, we have the chemical shift values in this case in ppm. So also we have what type of carbon, carbon that relates to. So we can see an example there of an aliphatic carbon being perhaps 5 to 40 ppm. And a similar looking table, but this is the proton NMR shift, chemical shift table. So we've got the values for the proton NMR chemical shifts and the types of proton, the types of hydrogen that are causing that chemical shift, that peak. So we can look at our NMR spectra and read off some information based on what the ppm value is. And then, of course, we do have the periodic table as well. Okay, so what's our approach to answering the question? So we're going to just overview it, and then we'll go into it in a lot more detail, step by step. So we'll need to extract details from each spectra. Remember, we don't have any spectra that we don't take information from. We don't have redundant data. So we're looking for information about what the functional group is, what the relative molecular mass is, and what structural fragments there are in the molecule. We're going to make notes of our findings as we go along. There's 4 spectra, don't forget. A lot of information that we'll be drawing from those spectra. So to look at it all and then at the end try and bring it all together without having noted it would be quite difficult. Then we need to piece the clues together. We need to consider the clue at the beginning of the question in the text of the question. So in our example, I was saying this molecule is an alcohol, or this molecule, compound X, has such an empirical formula. Okay, let's go into the detail. So we're going to work out the functional group first. That is definitely the first step. Without that, you're going to struggle with the other parts. Then we're going to find the relative molecular mass. And then we're going to determine the structural fragments. And I can't stress this enough, you need to note down this information as you go. For one thing, that's what's going to pick you up most of your marks, is your reasoning, the information that you've pulled from those spectra. Okay, so step 1, functional group. How do we do that? Well, we use the infrared spectrum to work that out and compare it with the data sheet. So, for example, we already saw a little bit of this. So we can look at our peaks that we have in our spectra and work out what bonds we have in our compound. And that's going to give us an indication. It's going to identify what the functional groups in our molecule are. So, for example, if we had a sharp peak between 500 and 600 wave numbers, that would indicate that we have a carbon to bromine bond in our molecule. If we had this broad peak at 3200 to 3550, somewhere in that range, that would indicate that we've got the hydroxyl group of an alcohol or phenol, and so on. Step 2 is the relative molecular mass, and we use the mass spectrum that we're giving in the question for this. What we need to know from this is the molecular ion peak is the peak with the highest M over Z value. The M over Z value is the molecular ion is the relative molecular mass of our compound. Usually. Why do I say usually? Well, almost every time it is. We're going to actually go through a tricky question after we've talked through the process where it's not exactly correct in that case, but we'll see how to resolve that. Step 3 is how we work out some of the structural information, and this is to do with the carbon environments. So here we're looking at the carbon-13 NMR spectrum. We're looking how many peaks there are, because this is the number of different carbon environments we have in our compound. In other words, how many chemically different carbons there are. And then not only that, we also compare the relative intensities of those peaks and compare the chemical shift values to the data booklet. This will give us information, firstly, about how many carbons there are in each of those environments, or at least the ratio of them. And the chemical shift values may give us some more information about what type of environment those carbons are in. So we would look at this table and we would potentially read off the chemical shift values and try to work out what type of carbon they pertain to. Step 4 is similar, but we're looking at protons now. So this is the hydrogen atoms within our compound, the protons. And so we're going to review the proton NMR spectrum that we're given in the question. Again, we're looking at how many peaks, and this is telling us a number of different proton environments, a number of chemically different proton types there are within the molecule. And we're going to note the relative intensities and any splitting information we're given in the question, because again, relative intensities will give us an idea of the ratio of how many hydrogens are in each of the environments. Splitting will obviously give us some information about how they relate to each other in position within the molecule. We don't always have splitting information given. We're going to also compare chemical shift values to the data sheet to see if they can give us any information as well. So we'll be looking at the ppm values that we can see for our peaks and trying to relate it to what type of proton we've got. And then it's the fun time. It's what I call jigsaw time. So this is where we're piecing all the information together. So we need to consider all the notes we've made for the information we've pulled from the spectra in steps 1 to 4. You know, if you've just looked at the proton NMR, you might have forgotten some other information. That's why you noted it all down. We're going to consider the text of the question. So in our example, it was compound X is an alcohol. And we're going to try and use logic to piece together those fragments with all the other information that we're given. How do we know when we've come to the correct answer? Well, the correct compound will be consistent with each piece of data that we've drawn from our spectra and from the text. So quite often you will be able to consider just a few candidate compounds. You can bring it down to perhaps two or three compounds that seem to fit most of the data, but only one of them will fit every piece of data, and that's going to be the correct answer. So just make sure you've not got one that's near enough but doesn't quite work with such a piece of data. Keep going and you'll find the one that does match every piece of data. Okay, so now we're going to look at an example question. And this one was actually sent to me by someone who was struggling a little with this. So this is a 2017 question from an A-level paper. I'm going to look at it a little more closely. So the question is saying, compound Y is a halogenoalkane. So a simplified form of the IR spectrum, the mass spectrum, the carbon-13 NMR and proton NMR of the compound are shown. Notice they're simplified. So we've got the infrared spectrum here with various peaks in it. Mass spectrum. We've got the carbon-13 NMR spectrum and the proton NMR spectrum as well, with their intensity values. So we use the spectra to determine the identity of compound Y, use evidence from each spectrum and explain how you used it. So step 1, just like the process we went through, in this one it's working out the functional group. So we'd use the infrared spectrum to work out what that group is. And we use the data sheet and make a note for each peak that matches the table. So here we've got a sharp peak at about 650 and a sharp peak at around about 3000-ish. These peaks here in this region are sometimes called the fingerprint region. These don't show on the table that we're given, so we don't need to make a note of these, but this peak and this peak do. So what have we got? Well, we had, if you remember, a peak at 650 and a peak at about 3000. It's a sharp peak. So that peak at 3000 is the carbon to hydrogen bond here, because that falls in this range. Now there is another bond type that falls in that range as well, about 3000. So one that falls between 2500 and 3200. But you can see a note here that that's a very broad peak, and you're probably familiar with the hydroxyl type peak that you get at that end of the spectrum. The peak we were looking at in our spectrum was sharp, so it's certainly not this peak. It can only be this peak. We also saw that there is a peak at around about 650, and the only one that coincides with that in our table is the carbon to chlorine peak, carbon to chlorine bond. Okay, next step was to work out the relative molecular mass. And remember we said that the molecular ion peak is the peak with the highest M over Z value. So in our mass spectrum, we can see that the M over Z values here, and we can see actually there's 3 peaks up at the molecular ion area. And if we're careful, we can work out that these are at 126, 128, and 130. So that's a little strange, but let's think about it. Sometimes you've probably been told that sometimes you see a small peak to the right of your molecular ion peak down, and this is due to isotopes, the presence of isotopes within the sample of the compound. Well, in this case, we already have we've just worked out that we have chlorine present in our molecule. And actually we know that chlorine is an element that has 2 common isotopes, chlorine-35 and chlorine-37. Chlorine-35 makes up about 75% of all chlorine atoms, and chlorine-37 makes up about 25% of all chlorine atoms. So if we had a chlorine atom present, we would expect to see 2 molecular ion peaks, one for molecules that had chlorine-35 and one for the molecules that had chlorine-37. But actually we see 3 peaks here, and that's a big clue for us. That's a big clue about this compound. It means that we must have 2 chlorine atoms present. So we have 3 peaks. We have a peak for the molecules that have 2 chlorine-35 atoms. We have a peak for molecules that have 1 chlorine-35 and 1 chlorine-37. And we have a third peak for molecules that have 2 chlorine-37 atoms present. And if we look at, these are actually spaced apart by the mass of 2, and we look at the intensity of these, we can see the biggest intensity is for the molecule that has 2 chlorine-35s, and the smallest intensity, the lowest intensity, for the molecule that has 2 chlorine-37s. All that adds up to support our evidence that there's 2 chlorine atoms present in our compound. So what we need to do is note that there are peaks at 126, 128, and 130. We'll come back to the relevance of that when we piece this together in step 5. Okay, now we're looking at the carbon-13 environments to help us work out the fragments of the molecule. So if we review the carbon-13 NMR spectra, we can see 2 peaks present. So that means there are 2 carbon environments, so 2 types of carbon, not necessarily 2 carbon atoms, but 2 types of carbon that are chemically identical groups of carbons within this molecule. Okay. So now we need to compare the relative intensities of the peaks, and within our experimental error, these are equal. And that means that there are an equal number of carbons in the two environments. So they could have 1 carbon in each, or 2 carbons in each, or 3 carbons in each type of environment. Now we look at the chemical shifts of those peaks, and we can see we have one peak at chemical shift 30 and one about chemical shift 45. And actually, if we look at our table, that doesn't really help us. These can relate to various possible fragments. It's difficult to draw any conclusions from that. But it's important to make the note. Okay. Now we're going to do something very similar with the proton environment. So we're looking at the proton NMR spectrum. And here again, we're going to look at how many peaks there are. Well, we have 2 peaks. So that means there's 2 proton environments, 2 groups of chemically identical protons. We're going to note the relative intensities of those peaks. And again, we can see that they are the same as each other, and therefore each of these 2 proton environments has the same number of protons. And we have no splitting information in this spectrum, so we don't have that information to help us, but it perhaps makes it simpler to answer the question too. Now we're going to connect the clues. So we've got the fact that we have a chloroalkane with possibly 2 chlorines. Well, I think from the mass spec, it's certainly 2 chlorines. We worked out the relative molecular mass is about 128. Remember, we had those 3 peaks. We have 2 carbon environments related to equal numbers of carbons in each. And we have 2 proton environments related to equal numbers of protons in each. Right, so how do we start piecing this together? Well, 2 carbon environments. So we must have an even number of carbons, because if we have 1 carbon in each of those environments, we have 2 carbons. If we have 2 carbons in each of those environments, we have 4 carbons, and so on. And we can make a similar conclusion about the protons, because if we have an equal number of protons in 2 different environments, then we either have 2, 4, 6, 8, 10, 12, or so on hydrogen atoms in our molecule. And because of the way the spectra are, we know that the compound must be symmetrical. Okay, let's go back to that relative molecular mass. So this compound, this empirical formula, C4H8Cl2, has a mass that fits quite well with our relative molecular mass. We'll look at that more closely in a moment. It could certainly be symmetrical. It has an even number of carbon atoms and an even number of hydrogen atoms. So that empirical formula fits with what we've said so far, with all the clues so far. But obviously that empirical formula can be more than 1 compound. So there's more than one that fits that. So let's look at it more closely. So firstly, we're going to look at that mass of 127, which actually, when we look at our mass spectrum, we'd had no peak at 127. It seems to fit in exactly the right area, but we had peaks of 126, 128, and 130. But our mass of 127 doesn't seem to work exactly with that. There's no peak at all there. So are we barking up the wrong tree or what? Well, no, we're not. The problem is, and it's not a problem, it's just a mathematical truth. We've worked out the mass of our molecule based on mean atomic masses. So we've looked at our spectrum and used 35.5 for chlorine. And of course, there is no individual chlorine atom that has a mass of 35.5. They're all whole numbers, individual atoms. So our mean molecule has a mass of 127, but actually no individual molecule does. Our individual molecules have a mass of 126, 128, or 130. So it does fit with this when we realize that actually our spectrum is actually measuring actual molecules. It's getting the mass of individual molecules and giving us the relative intensities of those molecules. And when we work out our relative molecular mass from the empirical formula, we're looking at mean values from the periodic table. So that's why there is a slight difference there. But it is not disproving our molecule, our empirical formula. It's actually approving it, if you will. Okay, so we were trying to work out which version of C4H8Cl2 this molecule could be. So I've drawn out the two symmetrical possibilities for this molecule. And we have at the top 1,4-dichlorobutane. So we have our chlorine on the end carbons of this chain. And down here we have 2,3-dichlorobutane. And this has the chlorines on carbon 2 and carbon 3. So both of these molecules fit nearly every piece of data that we've looked at. They've both got two types of carbon. So this one has, these two carbons here are identical. So that would be one environment. And these two carbons here are also identical to each other. So that would be the other carbon environment. Now with this molecule, again, these two carbons are one carbon environment. They're chemically the same as each other. And the two N carbons are the same as each other as well. They're two carbon environments that are chemically identical. Okay, how about numbers of protons? So here we have 1, 2, 3, 4 protons in one environment. These are all chemically identical to each other. And here we've got 1, 2, 3, 4 that are also chemically identical to each other, but different from the first 4. Okay, how about this molecule? Well, we have 1, 2, 3, 4, 5, 6 in one chemical environment. They're all chemically identical to each other. And these here are chemically identical to each other, but we've only got 2. So in this molecule, we have a 4 to 4, effectively an equal amount of hydrogens in each proton environment. And here we've got 2 in one environment and 6 in another, so a 1 to 3 ratio. Well, if we remember the spectra, our spectra told us that there was an equal number of hydrogens in each environment, and therefore it must be the top molecule 1,4-dichlorobutane. So in summary, what did we do? We noted all the data from the spectra. We made good use of the data sheet. We worked out first the functional group, then the relative molecular mass, and then the molecular fragments, and then we worked logically to piece it together. And that's the way to always do this type of question, and in this order as well: functional group, molecular mass, and then the fragments, the chemical environments of the carbons and the hydrogens. I'm going to invite you to suggest another lesson. So another subject, another question type, another topic from high school chemistry. You can just send me an email at matthew@chemistrymadesimple.net. That's me, by the way. And just tell me what the question type is. Even better if you could send me a copy of the question, take a photograph or send me a PDF of the question. And then, it's suitable for a session like this, we will set that up. What else I would ask you to do? Well, you can subscribe and follow me, and then you won't miss any of those lessons when they come up as well. So on Instagram, I'm at Chemistry Made Simple. You can DM me there as well. I'm quite active in the DMs there. You can also subscribe to my YouTube channel. I'll be putting this video and others into that. So again, Chemistry Made Simple, or you can visit my website at chemistrymadesimple.net.